All right. Good morning, good evening, or good night, wherever around the world you are. Friends, it's so great to have you here with me and with us, actually, for yet another fantastic episode of Microsoft Learn Live TV. And today I'm joined, but not only a fantastic presenter, but also a mentor, a role model, and most importantly, a good personal friend of mine, named Mark Brown. Mark, hi.
Hi, Alex. How are you? I don't know how much of a role model I am. I maybe model bad behaviors rather than good ones, but thanks for the shout out. I really appreciate it.
I've been really looking forward to having this session with you, actually, and I'm really keen on it and looking forward to actually teaching everyone here. Not sure about teaching as too much, preaching probably, designing data partitioning strategies. I know many in the audience haven't met you or myself personally, or probably don't even know who we are. So maybe let's introduce ourselves first. Mark, would you please be so kind and tell us who is Mark Brown?
Sure. So I'm Mark Brown, obviously. I work on the Cosmos-db team. You might have seen me around. I kind of lurk on Twitter for a better part of the day. I run kind of a near weekly podcast. We're taking a bit of time off, but we'll bringing that back soon. But I focus on a lot of our community and developer community efforts around Cosmos DB and help work on grading, awesome content to help people learn and get really good at using the service. And this content is part of some of the stuff that I've been working on. So I'm really excited to be able to talk about this in particular, because this is modeling and partitioning is a topic that I'm very passionate about because it's so critical to success.
It definitely is critical, and I'm sure you have a lot of fun stories to tell us from the customer learnings that you have done. I came across many of them myself. Now, for those
tell us about yourself now, Alex. I have to tell me.
For those of you who don't know
how have you been doing with me as your role model? I hope you're staying relatively.
I don't know what role model you're referring to. Maybe a bad role model like you've mentioned previously. My name is Alex Mang, obviously. I'm a Microsoft Most Valuable Azure Professional on the Azure Work category and MVP, also part of the Regional Directors Program. I've been working with Azure for the past 12 years, literally ever since Azure was a baby. I kind of picked it up, liked it, fell in love with it, really. And ever since then, it has been a love and hate relationship, more or less, but more on the love side, in all fairness.
You've been around for a long time, I remember, and it's great. So I'm excited. I hope people really love what we've got for them today. We're going to show them some pretty cool stuff. So
we definitely are.
Let's get started.
I do want to, before we get started, I do want to do a big shout out to actually our moderator today, Chris Hyde, a fellow data platform MVP. Who does not get the opportunity of speaking out loud, but yet he answers so the many questions that we have had in the previous episodes as well. And I do want to also emphasize this is a live session. So whether you're streaming in from YouTube or Twitch or LinkedIn or whatever platform you're on right now, make sure you join the chat window. Just say hi, tell us where you're from. I'm really interested in actually learning from where people are streaming in. It's really enjoyable and fantastic to see that we have people literally from around the world, and even seeing that in the chat window is so awesome. And big shout out to our producers, Jason, Laurent, community program managers, and all the many great people who actually put up the great work to making this series of episodes a reality. Now, a lot of you may already know and be familiar with the format. What we are doing here is that we're actually following the learning path for you to get certified, right? This is a training material. This is going to be a training session. We're going to teach you a bunch of topics. And today's module that we're covering and which we're following is the module with the same name, really, on Microsoft Learn, Designing Data Partition Strategy. But that being said, I would encourage you not to do the module on Microsoft Learn whilst we're doing the presentation, because you're going to get a lot more tips and tricks from the actual learnings that we have had from the real world, so to say. And it would be a fantastic opportunity for you just to ask questions and get your questions answered rather than actually going through the module. And that
By the way,
go ahead.
The other thing I wanted to point out too, and thanks, Alex, is this is part of a companion. There's another Microsoft Learn module that you should take at the same time, or at least before you do this one. So both those modules together kind of represent kind of all the concepts that we want to talk about here. So we're going to cover off on more of the advanced concepts with modeling and partitioning with Cosmos DB. But just want you to make you aware there is another module, very similar name to it, and you should take both those together, because together those will provide you kind of the foundation and the knowledge you need.
That's a fantastic tip. And in all fairness, Mark, I must say, I've been going through these modules, probably all of them, I guess, not entirely sure, so take this with a grain of salt, as I was preparing for the DP 420 exam, a developer specialty exam, which I think highly of. And I would encourage people, actually, whether or not they're studying right now for the exam, at least going through all of the modules available, because they're going to get a ton of fantastic learnings out of them. And whenever they feel prepared, they should also get certified as well.
Absolutely. Even if you're not going to get certified with Cosmos DB, and I think you absolutely should, but even if you're new to Cosmos DB, all the content we created and released as labs out on Microsoft Learn is a great foundation for you to get you started, so that you can be successful and just spend less time pulling hair out of your head like Alex and I have done in the past.
100%, 100%. And quick reminder, don't forget, this is a live interactive session, so please make sure that you head over to the chat window. Again, just say hi if you just joined, that's fine. Ask any questions you might have as we go through the material, and we'll answer all the questions as we go through. And even if we don't get yours live, our moderator, Chris, today is going to make, who's a subject matter expert, of course, he's going to get your question answered, and we'll be answering questions as we go as well. Mark, we have a lot of learning objectives today. This is going to be a very long module, in my opinion, at least. I know that for starters, we're going to talk about managing the relationship between data and entities by using advanced modeling and partitioning strategies. For some, even for myself, this might be a bit of a mouthful. So we're going to take this topic and bring it down to earth. But we also have other learning objectives, don't we?
Yeah. So one of the key aspects in understanding with a database like Cosmos is you can't apply relational constraints to things like collections or containers within Cosmos DB. So we use different technologies to do that. And in this session, we'll talk to you about how you use change feed, which is built into Cosmos DB, to help maintain referential integrity for the data within your collections, your database.
And once we have that covered, we're also going to implement pre-aggregating and denormalizing data strategies to improve data model performance and scaling. Again, might sound a bit of a mouthful. And in my opinion, many of these objectives actually go hand in hand. And whatever learnings you're going to get and take out of this module today, they're going to be fantastic for you to improve the performance, the reliability, and most importantly, the scalability of your data layer in your applications. And then last but not least, there's another one, isn't it?
Yeah. So, and this is kind of a really key optimization. We're going to show you how you can mix entities of different types and put them into the same container or into the same collection. Again, Cosmos is one of those databases where we call schema agnostic, right? Or it's NoSQL, but what we mean is schema agnostic, and that gives you an opportunity to do things that you could not do in other types of databases. And in this case, it actually provides some pretty interesting benefits and some key optimizations for storage and compute. So we will cover off on that topic as well within our session today.
So definitely a lot of learning objectives, a lot of things that we're gonna learn today. So let's not waste any more time and let's just go in, I guess, right?
Yeah. So if you want to share over to mine, I'm going to drive some slides here for us. So let's kind of get started here. And I want to get into first kind of an introduction for Cosmos DB. So at least as marketing likes to call it, azure-cosmos-db is Microsoft's fully managed NoSQL database for Azure. And what we mean by a NoSQL database is that Cosmos DB is both horizontally scalable and non-relational. So what we mean with the horizontally scalable is that we grow out. We don't grow up like you would with, say, a relational database or other types of databases that are not horizontally scalable. Being NoSQL database means that Cosmos DB is not relational, and that we don't put things like constraints on your database or locks on your data. You obviously can't do joins, at least across collections within Cosmos DB. And the reason we do this is that it allows this type of database to predictably scale. and provide predictable and low latency performance for your applications. And that's important because a database like Cosmos DB was designed specifically for these types of workloads where you're at, I guess, more or less cloud scale in terms of your size. Although I have to be, cautious here in that you don't have to have a cloud scale application to take advantage of a database like this, a database, or use a database like Cosmos DB for your applications. But this type of database provides the ability to grow to that sort of scale within there.
If I may, Mark, we've had this question in the past as well, where people are trying to do a comparison between relational and non-relational, and then they try to figure out, hey, why does even SQL Server have a new version? Why are we still focusing so much on improving SQL Server or whatnot? What's going to be the future like, or how does the future like look in terms of data? And I would like to pick your brain on particularly on this topic as to, should we move all our data in NoSQL, or specifically in Cosmos DB? Should we keep something out of it? Should any application just leverage Cosmos DB because it's the greatest and the newest and the coolest kid in town? Or what does the future look like?
That's a great question. I can say it a couple of different ways. Some things I'll say is, look, NoSQL databases were introduced to solve a particular problem. Go back about 12, 13, 14 years. And you have these internet companies that are coming online, and that could be, the likes of Facebook or Netflix or Twitter or others that are kind of running into kind of a brick wall with respect to how big they can grow their relational databases. In many cases, they were using things like MySQL. But regardless, these relational databases all kind of share a similar characteristic in that they can only grow to a certain size before you have to shard them. They just cannot grow any larger. Also, because as relational databases grow larger, latencies also get higher because it's swimming through an increasingly large binary file to go and find your data that's stored within it. NoSQL databases, particularly these distributed NoSQL databases, are designed to kind of deal with the kind of challenges and issues that developers back then kind of faced in terms of how big can they grow, right? And when you have a database that is designed to provide little tiny databases that you can then scale out by just adding more nodes to it, you kind of eliminate the problems with how big you get. You just keep adding on to them or scaling out, and you can grow to functionally infinite size. The trade-off there is that you need a key, a shard key in this case, or a partition key to help find that data or to locate it, right? And you can look at a shard key as kind of like an address for where your data is stored. The other trouble too is with this type of database was also the kind of the latency. And that was kind of another key aspect for why NoSQL, and that not putting locks on data or enforcing all these relational constraints made it possible to build a database that you could predictably have high performance for. And consider this, you could have a database for Cosmos that's a couple of meg in size that's providing single digit latency, or could be petabytes in size with the same type of latency. And that's not possible with the relational database. But it is with this one.
I must say, emphasis on single digit millisecond latency, like single digit millisecond latency, even for petabytes size of data sets.
Right.
I remember when I delivered a presentation several years ago on SQL Server Elastic Scale, which is a completely different technology, on the purpose of sharding your data and figuring out how to simplify the process of sharding and merging and splitting your data sets into several shards or bringing them back in respectively. And even though it was a conference presentation, all right, so 50 minutes, it was regarded as a 400 plus level, because even though there's a tool and a bunch of PowerShell scripts, it is a very complex process. SQL Server, whenever it was designed several decades ago, was not designed for this amount of data. I mean, 30, 40 years ago, data, even in terms of gigabytes, was costing probably hundreds of dollars to maintain, not even relationalize and have the indexes on. And now we're talking about petabytes of data, not terabytes, petabytes of data. And so obviously technology is not necessarily overwhelmed, but is not initially designed for that, right? So Cosmos DB definitely has a selling point there.
Consider this, the design goal for a relational database back in 1970, when you had the very first relational database proposed by, what's his name, at IBM, designed to optimize for storage, right? Think about this, is that like 100 megabytes of storage back in like 1970 probably cost you like $500,000. So what are you going to do? You're going to design a database and propose techniques to do things like normalize data to reduce duplicates, because you want to reduce the amount of storage necessary. So the cost of storage relative to compute in 1970 was very high for the storage and very low for the compute relative to each other. Now, fast forward 50 years, right? 50 plus years, the economics on this are totally flipped, right? I've got a cell phone here. This thing's got a terabyte of storage on it, and it only cost me a few $100, right? So that's a terabyte. Now, in 1970 dollars, I don't think there's enough gold reserves in the world to pay for the storage that would have cost me to buy a terabyte of storage. These days, I get it for a few $100. So that economics, the cost of compute relative to storage, is now completely inverse, right? So duplicate data all you want. That's fine, because what you're doing and solving for this type of database is compute usage. You want to reduce the amount of compute as much as humanly possible. And by that, what we mean is reducing the number of requests to the database by modeling it such that the data is ready for you to consume or to use or to write all at once, or in as one or as few requests as possible. So that is why, kind of the why of no SQL databases and what they were designed for, and understanding both the economics of what was driving them and also the technical benefits or limitations of relational versus NoSQL.
I still vividly remember when I've learned about databases initially, relational databases, of course, back in high school. The big selling point was normalization, like you have mentioned previously. And the idea was, well, this might be a big word for some, but normalization is all about ensuring that you don't have duplicates. And coming back to Earth, even though we're going to talk about Cosmos, down to Earth level, what this means is that if you have a product, you're going to have an identifier in the relational database for your shopping basket referencing the product, and then one for the order details referencing the product, and wherever else, right? Whereas in Cosmos, we actually want to emphasize on not having as many requests as you have mentioned, right? And rather just having all the data readily available in a single shot. So not worrying as much about doing references and joins and stuff like that, which would just increase the CPU consumption probably.
That's right. Those techniques we're going to talk about, and you'll hear them, like denormalization. I'll talk about it in the next slide or so. But all these techniques are designed to provide you the skills, the tools, the knowledge necessary to model for an effective and efficient database within Cosmos DB. And frankly, there's no better way to start than we're going to take an existing relational database. In fact, we're going to take AdventureWorks 2017, or at least a subsection of it, and we're going to remodel that from a relational database, a SQL Server type database, into a Cosmos DB, into a NoSQL database, and show you the techniques and the tips and the tricks on how we're going to do it. And I think you're going to be blown away when you see just how awesome this is. So back to our scenario here. So it's AdventureWorks. So our scenario here is you've been hired. You're going to go work at an e-commerce startup, and you're replacing a guy designed a whole new shopping cart e-commerce database experience, but he built it doing relational modeling, so it's designed for a relational data store. Let's say you've got a new CTO, and he says, "Hey, we're going large, big and large e-commerce style, so we need a design that's going to scale, and it's not going to provide us any problems as we go from 0 customers to 1 million customers. And we want to be able to do that in a way that we can quickly and easily and efficiently scale from 0 to 1 million on there." So that is kind of our scenario here for us. And so let's talk about what we're going to be doing. So in this module, we're going to redesign this relational data store to work with Cosmos DB. And so some of the things we're going to talk about in here are denormalization. So of course you understand what normalization means, right? You want to eliminate the duplicates. In denormalization, we're doing precisely the opposite on that, and we're staging data such that it's ready to consume, or we're writing data such that it's all ready to store. We'll talk about referential integrity. This is actually a thing in a database like Cosmos and a NoSQL database, but we don't enforce it using the same technologies and the same techniques. And so we'll talk about change feed and how you use change feed to maintain referential integrity. And we've got some master data and also a product table or a container that will show how we maintain that referential integrity between 2 different collections within a Cosmos DB database. We'll also talk about another concept of combining entities, right? So this is the concept of, I have a NoSQL database. I don't enforce schema. because I'm a NoSQL database, right? You define schema in your classes, right, using POCOs or plain old C# objects, or POJOs if you're a Java developer. And we can combine different entities into the same collection, in the same container. Now, there are some scenarios as to how or why or when you can do that, and we'll go into those so you understand when you can apply that technique and use it. And then the last one, and this is super important, is the concept of denormalizing aggregates. And kind of the key here to understand is Cosmos as a database is designed as an operational data store, meaning it's really built for high volume, high speed OLTP types of operations, of transactions. It is not designed necessarily for use in doing kind of heavy OLAP-y types of queries, right? Where you're going to say, hey, I want to see, give me, and the scenario we'll go into here is, give me a grand total of all the orders for every one of my customers, right? And show that to me in there. Now, that would require going and querying all the customers and then all their orders and then counting those up and then returning the result. So we'll show, at least this is a technique, how you can use denormalizing of aggregates. And then we'll also combine that with another cool thing we'll show you, which is transactions, and how you can combine those things with the model we've designed to be able to provide the ability to serve these types of queries and do it in a very, or at least a more cost-efficient manner. Okay, so let's see how, I got a question or a comment here. Hoping they cover how to design better to avoid the 20 gigabyte partition size limit. Yeah, we can talk about that. Don't know exactly.
That's going to be an actually good. That's a good call out, I would say, because when you think about data modeling to begin with, you think about your logical partitions and how you spread your data. And I know that a lot of people are thinking about the kind of relational strategy or mind mapping, right, around the way they would structure their logical partitions. And this couldn't be any less true, right? They shouldn't do that because they should always try to avoid hot partitions. So maybe you can introduce a topic such as hot partitions later on, and how we would want to like fan out all the queries when necessary, especially when you have such distributed data. We could also introduce topics such as high cardinality and picking your partition key based on high cardinality, which again is a term that many people might not understand. So I guess we probably have some additional goals to add to the slide deck there.
Yeah, I think you're right. And I think it's a fair question. I think this is a question I see frequently when they struggle. I mean, 20 gig is not a large amount of data. And people, obviously, when they're coming up with having to design and dealing with a really tough concept, like how do I partition my data such that it scales, would often prefer to just punt on that if they could and not have to design or accommodate it. Agree that 20 gig is hard, and that the premise of having to do that is a challenge. The only thing I'll say is that if you put in the work and the effort, what you get in return is awesome scalability within your application and your database. I know it's a small amount, but the benefit of that is that it provides higher elasticity at lower scale, if you will. So you're going to get more efficiency than if you say had, I don't know, 100 gigabyte partitions. The cost of compute over that amount of storage is going to be higher. So at smaller sizes, you're not going to get as much cost efficiency as you could as if you had smaller shards. That said, we know there's, we'd like them to be bigger too. There's some other implementation aspects behind this. What I can say is Alex is right. We want you to think about the access patterns to your data such that you have high enough cardinality for the partition key values, such that, and also that the access patterns apply them such that you can spread them evenly in a high write volume, because that's the whole point. Is when you provision throughput for the database, it's going to provision physical storage and physical compute. That partition there, a partition is really just a piece of compute with some storage on it. And your objective is to make sure that if I provision compute, that I'm consuming it, that I'm being efficient with it. I don't want to provision like a G series VM and then play solitaire on the thing, right? It's costing me $10,000 a day, and I'm clearly not using all the compute and CPU and IOPS that I'm paying for. Same thing applies to a database like this. If I'm going to provision that amount of compute, I need to make sure that I'm being efficient and that I'm using it, consuming it. Otherwise, I'm wasting money. Anyway, let's keep moving here. We are going to talk about this. I don't know who the person is, but
we're definitely going to cover it.
Keep watching. Okay, so all right. So in this module, when you're done, you're going to understand and be able to understand how to manage the relationships between entities using the advanced techniques that we're going to show you here today. Also, techniques on how to manage referential integrity using technologies like change feed. We'll show you how to do things like pre-aggregating and denormalizing of data within there, so you can provide more efficient ways to be able to fetch and or write data within there. And then finally, we'll show you techniques for optimizing the storage of compute by mixing different entity types into a single collection, into a single container. So let's see. I guess next is off to you, Alex, and we're going to start by going into denormalization of data within your model.
So we effectively have 4 big pillars in this conversation. And the first one is indeed denormalization, or how you should stop thinking about your data by placing so many joins and references and foreign keys and whatnot as you would normally do in the relational database. Because in this particular episode, we're going to look at the product table from the relational database and model it as a NoSQL database, or as a NoSQL data structure instead. And we'll be looking at the many-to-many relationship of the product table. And as you can see, for instance, we have a relationship as many-to-many again to the product tags table, right? The references here that we have is this is the product table, this is the product tags, this is a many-to-many relationship because many tags can be used by many different products, of course. We do have a small snippet here, a JSON document, which is trying to emphasize how the product table actually looks like. And then obviously the product text table would be somewhat similar, where you have an identifier for the product identifier and one for the tag identifier. Now, the initial model for the product table includes only the fields from the relational table, of course. And if I were to zoom in, you're going to see real quick every single property that you would have there. But for the e-commerce application, it's going to be very likely that you're going to display the product category name whenever you're going to display the product page, for instance. Or you also want to display and query for products by the product tags within a product category as well. And this can be done in either of the 2 ways. You either store the products in a product tags container, or you can embed your tags in the product tags container. So you effectively have the information related to the categories and the tags respectively within the document representing the product. Now, obviously, there's always a sweet spot, because you could either say, yeah, I'm going to embed everything in a single document, but then you're going to have another limit, which is the document size, or you're going to have a document where only statistically 25% of the attributes ever change or ever have to be queried, which would be a bad decision for you to embed everything, right? So there's always a sweet spot. Now, because there are fewer tags per product than actual products per tags, it makes sense to embed the product tags into the products table. Had it been the other way around, you'd probably do the other way around, where you would embed the products within the product tags table. But obviously, that's not a realistic scenario, at least not for e-commerce.
The other thing, too, is you could also consider doing it the other way, too, if you were going to frequently query by tag name. Right. So you want to say, okay, give me all the products with this tag. Like, we've modeled it this way in here because the scenario is that you're gonna frequently query or access this by querying the category ID in there. Oh, and I kind of spilled your coffee with because we haven't picked a partition key yet. But just to cover the scenario, like, it's not uncommon to represent data twice, right? Like, you're denormalizing data. In this case, you could have a product tags collection that was product tag with an array of products within it, right? And that's totally normal. And yet another way you'd want to maintain a referential integrity that we'll cover later. But you want to design such that you have efficient ways to serve queries. So, and it's always a matter of the frequency of concurrency. So in our scenario here, we're going to be querying frequently by products showing by product category ID, right? That's the scenario we've defined. But if you had a lot of searching or querying by tags, then it would be totally fine. And it's totally acceptable to model another collection and then model it such that it's there to serve up products based upon the tag name within there. So anyway,
and emphasis that it doesn't have to be either or, right? It doesn't have to be
yeah.
embedded within the products or embedded within the product tags. It can be both of them, as you have mentioned previously, especially if you have a scenario where you have both queries running, where you're querying for products or product categories and you want to see the tags, but the other way around, where you're querying for tags and want to see the products
Yep.
within them. So having both and maintaining referential integrity is totally spot on, especially for the NoSQL world. Now, because as I've said previously, in our scenario, we're going to query the products by the category, and because there are fewer tags per products than product tags, we are going to focus in this scenario where we embed everything within the products table. And there is a one-to-few relationship between each product and the tags, which makes a good case for embedding. We also store the product data within the embedded tags in the new product container, because we're going to have a new product container. So new product model will appear as you see it in this diagram right here.
Should you define what one to few means? Because I find some developers are confused. What the hell do you mean when you say that? So sorry for a little French snuck out there. But what do you mean when you say one to few?
So that's actually a very good question. We have several relationships whenever we talk about data, right? We have many to many, one to many. One to few is one that actually comes up, especially when we think about NoSQL, unless I'm mistaken, but feel free to interject here. Whenever we have a major magnitude of a difference between the two different entities that we're going to talk about, where you're going to selectively pick some entities that have a relationship with the other entity out of a larger set, we're going to talk about a one to few. But I'm not sure if there is a very if there is like a concise understanding under what few is versus many, especially in terms of the context of the size of the data set.
The way I define it is one to few is a bounded one to many relationship, right? Like in an e-commerce scenario, a customer could have many addresses. Now they may have, well, certainly their own address, but they may have their mom, their sister, their brother, grandma, grandpa. But it's not an unlimited list. It's not thousands or tens of thousands, right? Which may still be bounded, but it's an insanely large number. That is what I call one to few, is when it's a bounded one to many relationship. Versus one to many, which I take to mean that is largely unbounded. In my kind of go-to scenario there is, say, comments on a blog post. Yes, many of them are likely bounded or a small number, but you can have occasional or occasions where, say, a blog post just goes viral or takes off, and you've got thousands and tens of thousands and hundreds of thousands of comments on there. So that's what I call kind of the unbounded. So anyway, so that's how I use one to few to help kind of the mental model I use to help describe that to users, and generally it works.
Yeah, that's a very good explanation. And in the context of this presentation here, of this particular scenario, you only have so many tags per products, right? But you're going to likely have hundreds, thousands, tens of thousands of tags overall, especially if you're a big shop like, I don't know, one which starts with Amazonian.com or whatever. And you're unlikely going to have all of those tags applied to the product, but only a handful of them, like you've said, a bounded list, a bounded reference.
We'll just say the tropical forest retailer.
The tropical forest retailer, that's a good one. Now, next, the other very important topic is selecting the partition key for the container. And again, you need to look at the operation to be performed to decide on a partition key. And I know as a fellow developer, this is always a very tough decision to make, because by the time you're writing it and you're developing your data model initially, caveat, you need to pick your partition key by the moment you create your container. You can't change it afterwards. You're unlikely going to have the answer towards the question, what kind of an operation will this UI ever do, right? Things do change. New features are added, so you may not even pick the right partition at the right time. But the good thing is the flexibility that you're getting, because you can always have duplicates of your data, move your data, strategize your remodeling your data, and so on and so forth. So your options are either to create a product or to edit a product. And as customers would navigate your e-commerce site, they will offer, if you just try to mentally think of it, they'll often do so by looking at the facets, the list of categories on the left side, pick a category or product category, and then probably they're going to use a filter to filter down on that category. Like look at make, model, manufacturer, manufacturing date, maybe a price range or something along those lines. So the category ID, the identifier here, might be a very good partition key that lets you retrieve all the products within a category efficiently. So if you embed the tag IDs, you can also get all the IDs in your many-to-many relationship between the products and the tags as well. However, when you query for products, you need not only the product data, but you need to display the category name. You need to display the tag name. And when you query for products, the question is, how do you return the category name for each product and the names for that product tag? Now, currently, especially on the premise that you're within the relational model, you display the product page for a category, and you'd run a query that retrieves the product container, returning all the products. You do another query that retrieves the product category information, like the category name. Then you run another query to retrieve the tag names based on the products that you're displaying, right? So you're doing a bunch of different queries just to display a single page. And the number of queries that you're actually doing can be dynamic, especially with the many-to-many relationship. You don't know how many queries you're going to have to run to determine each tag name, because the list of tags per product can be well, it's going to be a few many-to-few or one-to-few relationship, but it's still going to be a dynamic number. So running all of these queries could work, sure, but this approach is anything but scalable. And you should always keep in mind that in NoSQL databases, there are no joins between containers. Caveat, there is a bit of a join in Cosmos-DB, but I'm going to keep that for a different conversation. So the 101 should be for you, the 101 lesson should be that joins are not an option. And you should also remember that for NoSQL databases, the objective is always to reduce the number of requests that you're doing by modeling the data in such a way that you can fetch all of the data necessary with as few requests as possible. And that's why we call the solution denormalization. Whereas in relational, you'd normalize and you'd, well, prevent duplicates from ever happening. Over here, we're denormalizing, and we're absolutely fine with duplicate data as long as we keep it in sync, as long as one change updates all of the data everywhere else as well. So you can optimize your data models to ensure that all the required data for your application is always ready to be served by your queries. And that's pretty much it. That's the big selling point. I know denormalization is a tough word for some, but if you come to think of it, it's not such a complex approach to.
I can't stress enough how much I know relational developers just grimace at the thought of having to do this to data when they're modeling at it. I just want to let you know that I understand.
You're not alone.
It's a struggle. You have to not trust your instincts in terms of how do you do it for a database like Cosmos. We're showing you these techniques because too many people I know have walked into a scenario or a space like this and tried to apply relational thinking to designing and modeling their database and failed miserably because it doesn't scale precisely for that reason, right? Like you could keep these all in separate containers and then run one or more queries to get them, but you will pay a lot for it and your performance will be very, very slow. So we understand. We would never lead you down a wrong path, but these are the techniques we've learned and we know based upon actual usage in there. So, okay, what's next? Oh, it's back to me. All right.
Managing referential integrity by using change feed.
Let's talk about that. So I earlier, and also Alex mentioned, that you can use that you have to maintain referential integrity, right? Like you have data that has to be stored in multiple containers, particularly like reference data. An example would be, say, your product categories. Now, in Alex's example, he was taking the category ID and the category name and putting it in the product category table. However, you still need a way to maintain product category data separate, if you will. Like it's got a name. It may have other attributes as well. I think for our purposes here, we just have an ID and a name. And then the same thing with tags. And you need to maintain those separate from the collection or the container where they're used. In our case, it's the product container there. So you need a way to be able to maintain the referential integrity between those things. What if I change a name for a product category? How do I make sure that is reflected in all of the products within that category? Well, I'm going to use this thing called change feed. Now, change feed is functionally, I guess you could call it an API. But more technically, it's kind of a mechanism that provides kind of change data capture functionality over your data within Cosmos DB. So as data as written or updated into Cosmos DB, change feed will make note of that. And then if you write an application that listens to change feed, you will get notifications of changes to data within your collection or your container via a delegate that you define when you write code to listen to the change feed within Cosmos DB. So here, what we're going to do is we're going to create a little routine, and I'll show you this a little later in our exercise. But we're going to listen to our product category container, and then we're going to change the name of one of those categories, and then we'll watch how do we implement change feed such that we can replicate that change from our product category collection into our product collection, and then replicate those changes from one over to another to maintain that referential integrity between the two. Okay, Alex, back over to you.
So previously, we did talk about this idea of embedding data and combining entities. So this is going to be a short topic, especially because we're like over 40 minutes in, and I know what Linus's Torvalds famous words are: "Show me the code. Enough talking. Show me the code." So we're definitely going to get to that, and we're going to have a long presentation, hands-on presentation in a minute. But even though you get to the point where you're nearly finished modeling your database for your e-commerce application, there are going to be some very important concepts to demonstrate. So let's maybe look at the sales order entities. Again, canonical example, e-commerce here. But as with any other entities, you want to look at the operations first. You need to understand your business logic. You need to understand the overall requirements that you have. And then you would decide whether to embed or reference your related data. In this scenario, the sales order detail table, usually we as developers call it the SOD table, makes a great candidate for embedding. And this is because items in the order are not so unbounded. The data is always going to be inserted and read together. So you're most likely going to embed sale order details as an array, probably, of your sales entities. And you'll probably store your new data in a new container. Let's just imagine this would be called sales order. And next, you're going to have to choose a partition key, just like the same exercise we did previously. Now, because you will always search for sales orders, most likely by customer identifiers, again, make a suitable partition key for your container. It might be a different one as well, but the choice of the customer ID here would give you a single partition query for an operation that will run frequently. And I want to emphasize one thing, which is super important. When we say that you're picking a partition key, it doesn't mean that you're going to automatically generate physical partitions that are going to hold your data. You should think of these as logical partitions. I know, as a fellow relational data lover back in the day, this idea of logical partitions, high cardinality on logical partitions, not having them structured or thought of as pages or whatnot, or AKA physical partitions, which go up to 20 gigs, by the way, in Cosmos DB, is something that is difficult to wrap your head against, right? But here's the deal. If you create many, and I mean by many, like a magnitude of many logical partitions, that's fine. We love you still. And we really want you to have partitions which would follow the logic of your business, as in you're querying based your orders based on the customer ID should be your key, because you're not querying on anything else. And then you can just read a full partition out, a logical partition again, and retrieve all that data that is part of your one customer. And understand all the orders they did. So at this point, we have modeled all the relational entities for the NoSQL database. So let's probably take another look at where you can make some further optimizations. And one of them, in all fairness, is one thing that you might also have noticed, Mark, is that with the sales order container, it shares the same partition key as the customer container. Right?
Yep.
So the customer container has a partition key of ID, and the sales order has a partition key of customer ID, but it's the same data. So where data share a partition key and have similar access patterns, they're actually good candidates for being stored in the same container. As a NoSQL database, azure-cosmos-db is schema agnostic. Again, something that the relational database lover would have to wrap their head against a bit. Because mixing entities into different schema is not only possible, but under these conditions is actually a best practice. Again, the emphasis here is that the data itself has different schema, but Cosmos DB is schema agnostic, aka doesn't care. So you just mix and match it almost as in a hot pot everything. But the reality is that the query that you're running is going to make the major difference in understanding what type of data you're retrieving. So first, we need to add a customer ID property to each customer document so that they have both the same property with the same name. Customers will now have the same value for the ID and the customer ID, but that's fine. And next, you need to find a way to distinguish which document is a sales order and which document is a customer. And usually, you're going to add some sort of a discriminator property called type or whatever you pick. But the type would have a value that you hard code in your code and say, yeah, this is a sale. Yeah, this is a customer. And when you run your query, it's going to be retrieve me all the data where type equals customer and identifier equals whatever, right? And then you have your customer data. Or retrieve me data where type equals sales and customers equals this. And then you have all your sales, because remember, this is a large partition. And with these changes, you can now store both of the customer data and your order data within the new customer container. And again, this is a best practice. This is part of the way you should think about NoSQL and in particular Cosmos DB.
So important, Alex. Again, it comes down to the access patterns. Like, well, first of all, do they share a partition key? Like that has to exist before you can even consider doing this. Yeah. And in this case, they do. They share customer ID as a partition key, which makes sense because the access pattern for this is I'm a customer. I'm going to look myself up by customer ID, or I'm a customer. I want to look at my sales orders. So in either case, I'm passing both of those. And in some cases, I need them simultaneously. Like if I'm logging in, maybe the first thing I'm doing is I'm going and hitting my orders page to see the orders I've got. So I could easily write a query in there that's single partition, grab me the customer document, and then grab me, I don't know, my first 10 orders or something like that, and then show them on whatever screen, or grab all of them or whatever. But that's, again, it comes down to how are you using the data within your application. That always is going to drive how do you want to model it. And in the cases here, we can save money on storage by cohabitating both of these entities into a single collection rather than splitting them into two different ones. But also, we can query them at the same time, same exact request to get that data or some flavor of those two entities together within a single query.
Absolutely. And then I think it's back to you on denormalizing aggregates.
Back to me. So one more optimization we want to do is we want to do something we call denormalize aggregates within the same container. So idea here is, okay, our model's nearly complete, but one of the operations that we wanted to take a look at is kind of like an OLAP-y type of query. But I wanted to get maybe my top 10 customers and see who are my top 10 customers by sales orders. So the query I'm going to have here is select top 10 star from C, where C.type equals customer, right? Because now, as Alex mentioned, we've introduced this new discriminator property that allows me to select just the customer entities out of this collection. And then I want to say, okay, then order by the sales order count descendings. Now, normally what I would do is I would have a query for my customer table and then join that to my sales order and then do my top 10 or do my orders aggregate sum of there and then do a top 10 out of that result. Now, Cosmos, you cannot do that type of thing, right? We mentioned that you can't join across collections. So we need to find a way to be able to materialize that aggregate and store it in a way that I can quickly and easily query for it in Cosmos, keeping in mind that this is an operational data store. It's not an OLAP database, right? It's not designed for running big fat OLAP queries. However, you can do things, and we're going to model this such that you can provide that data, that functionality, but there's just different techniques for how you manage it and how you get there. So in this scenario here, we're going to introduce a new property called sales order count. And now the way this works is now that we've got our data that is stored in the same collection, right? As Alex mentioned, we're cohabitating both those different entity types. We can also, because this data lives within the same logical partition, we could take advantage of transactions within Cosmos DB. Now, that's right. I said we're a NoSQL database, but Cosmos supports transactions. As long as they're scoped, meaning as long as the data sits within the same logical partition, meaning that the value for that partition key is the same. And in this case, it's going to be a customer ID. So the scenario here is I'm now going to introduce this denormalized aggregate as a new property, sales order count. I'm going to persist it in my customer record. So each customer record will have this new property. And then every time a new order is created, I'm going to increment that value and save it back to the customer record. At the same time, I create and store a new sales order, and I'm going to wrap all that into a transaction such that all of it completes successfully or none of it completes successfully. Okay, let's see what else here. Okay, so with that, then we're going to finalize our data model. So what we've got here now is we've got 4 different containers, right? Remember, we started with like 13 different collections where we had 3 customer, we had product, we had category, product, many in there. So that's 7. And then we had a sales order and a sales order detail. So I had 9. So we had 9 collections. Did I get that right? I think it was 9.
I think it was 9, yeah.
Yeah. And now we've gone from 9 different separate tables in a relational world down to 4 different collections or containers within a NoSQL world. So we've got our customer container, which is partitioned by customer ID, and that contains customers and sales orders, which have a discriminator property on them. We also have a product category or product container where we've denormalized our product category name as well as the tag IDs as an array within each of our products. And then we've got 2 different kind of lookup. This is like master data. We've got a product tag container here on the top right, and then we've got product category there on the bottom right. So that's great, but we can actually get a little bit further here. So one of the things we're going to do, and I don't know if you noticed, but and actually, I guess we didn't talk about this, did we? But I'll talk about it now. We can take product category and product type and merge those into the same collection, into the same container. And the way we can do that is to use the technique we introduced earlier with orders and customers and implement a type property. And in this case, for categories, we'll have a value of category for the type property. And for tags, we'll use the value of tag in there. And on top of that, we'll make that the partition key. So all the product category data sits in one logical partition and all the tags sit in another, etc. And now we can do is we can merge all these into a single collection and get even further savings on the storage because we've reduced having yet another collection within our database. But we've also simplified access to it. And not only that, we can also simplify things like referential integrity, because now what I can do is instead of having to create a new change feed listener for each of the different collections, I can do it on a single one and then listen for changes across every collection I put in there. And I don't have to stop with these 2. Like if I have a user interface and I want to hydrate things like drop downs or list or other things in there, I could store it in here and just query that at the beginning. Or if I have data that I just want to cache up in memory or something like that, store it in here, right? It's generally data that you can use once and then just keep using it over and over again.
If I may, I do have one point I would want to make here, namely the fact that the reason for why we picked those 2 and not any other is that there's an expectation that these won't exceed the size of a single physical partition, which is 20 gigs. Because had you had larger data sets, you'd probably wouldn't want to merge everything together, because then you'd find yourself in the position of having to fan out a single request to multiple partitions and thus increasing and parallelizing your RU consumption.
That is absolutely correct. And very critical is before you do this, make sure that the data you want to move easily sits within a 20 gigabyte range of data, which is actually quite a bit of data when you're talking about something like a lookup table, like a product category or product tag, where you've got just a few bytes of information basically per document in there. So yes. Okay. So, and now you can see I've got my queries here. This is how I would query for each of those coming out of there. And then finally, here is our final design. We've gone from like 9 relational tables down to 3 containers within Cosmos DB, all designed to scale for you and designed for efficiency in terms of storage. So yeah, are we duplicating data? Yep. But we're also reducing it where we can as well, or at least where it makes sense. But really the overarching outcome that we're looking for here is to have high efficiency in terms of request, so low compute usage for getting the data, and then also efficiency in terms of the partition key design. This model will scale as we grow larger. So the more customers we get, the bigger it gets, the faster, the more it has to do. This will scale within there. So I think that is it for slides. As promised, Alex and I said we were going to show some code. I know it took us a while to get here. We've got some code we're going to show you.
We definitely do. So we're actually starting with the scenario that we talked about. And this exercise that we're going to show you is the same exercise that you can go through yourself when you will get to cover the when you'll do that at your own pace, the Microsoft Learn module. But in the interest of time, we actually fast forwarded a bit. There is a data feeding or a data sourcing step. There's a step which will have you deploy a new Cosmos-db account, feed us some data, as I've said, and whatnot. And eventually we're going to get to a very similar Cosmos-db account, obviously with a different name than the one I have, which will give you the opportunity to measure the performance cost, for instance, when you're denormalizing the data. And this is literally what we're going to start off with. So as you can tell, I have 4 different containers here, 4 different databases, my apologies. One of them is called database v2, and this is the one I'm going to focus on right now. So even though I'm not in the Azure portal, this is Cosmo Azure Com. I am just highlighting everything in full screen, so I'm taking away the Azure portal drop downs and bars and menus and whatnot. It's still the same UI. It's still the same experience that you're getting here. So I am already showing you the product category container right here, heading over to items. And now I'm first going to open up actually and write a brand new query. So what I'm going to do here is that, where's that? New item. I just opened up, I'll be honest with you, I just opened up this UI. I'm just realized that there is no, where's the new SQL on this one? There's none? No problem, I can write this down myself, can't I? So in the product category, what I'm going to do is that I'm going to query for every single document that is of type category and also pull its identifier. And the purpose of doing so is to actually simulate how the application would act in terms of Cosmos-db to retrieve a single category information. And it's going to be necessary for rendering that product web page we talked about previously. And this retrieves me or gets me back a bunch of information related to that one document. You know what? I'm actually going to go back because I do want to show you one more thing. I'm going to go back to the Azure portal, open up the Azure the Data Explorer, even though it will not have the same fantastic UI the other product has, and open up a SQL query instead. So same query one more time, going to execute it. And the one thing I do want to show you here is that I will have to zoom out regretfully.
Sorry.
Hey, if you know somebody in Cosmos-db, maybe you can give them a hint.
I might have an in with someone over in the portal team.
So the request charge only for retrieving the category information is roughly 2.92 RUs. So I'm going to try to keep this one in mind. But I only have the category information, right? So the next step for me would be to retrieve the product information, obviously. So I would have to head over to the product container, then open up a new SQL query for this one instead, and now just retrieve the information of all the products within the same category I previously queried. So I'm going to execute this fellow right here. So now for this query, I have a RU consumption of 2.89 RUs in total. So if we are to sum these up, the RU consumption for retrieving category information, the RU consumption for retrieving the product information, we're already a bit over 5 RUs, and we're not done yet, right? We still have to retrieve information related to the tags. So for that one, I'm going to head over to the product cat tag container, open up a new SQL query window in this category, and I'm going to say effectively a filter or predicate along the lines of retrieve me all the products where the type is going to be tag and the identifier is going to be either of these ones. And why do I do that? Because for the first product I'm querying right now, I do have 2 tags, and these are the identifiers of those tags. And this is going to give me a chargeback of 3.06 RUs. But keep in mind, I need to run this query for every product that I'm going to display. So I'm going to run this query for the first product. I'm going to run this query again for the second product, and so on and so forth. So the number of RUs you're consuming is going to dramatically increase. But if you head back to the query results we have had here, we have three different products returned. So for these 3 products, we would have to run 3 different queries just to retrieve the tags. That's, if you ask me, a bit outrageous, to say the least, because we're going to dramatically, exponentially, really increase the number of requests for just displaying a single web page. And if you start to sum these up, there's going to be 2.89 plus 2.92 plus 3.06 times 3 probably, or something along those lines. And you're going to easily get to 15 RUs just for rendering a single web page. And remember, electrons have to move around the wire, right? So you're going to have additional latency involved, and everything is going to eventually feel sluggish and slow in your e-commerce application. So you're definitely not going to be offering user experiences as to the tropical Amazonian forests.
And that's right. And it's also expensive because the first thing people do when they sense the performance is not good is they jack up the throughput. And then
absolutely.
Yeah. So now they're paying more. It had no impact. At least it wouldn't in this scenario. So they're even more frustrated.
They definitely are. And when people are forced to do the last thing we developers want them to do, which is they refresh, which is going to just charge you again the same thing you were just charged with.
Oh, that was slow. Let me F5 that, and then over and over.
Absolutely, it's going to fix it, won't it? So in database v3, and this is something that if you go through the module yourself, you're going to get it as well. We have remodeled the entire container. Now we have a single container product where we have embedded a bunch of data. So if I actually look at one of these documents, you're going to see that within the document I already have the category name. So I don't need to run that query again. I have all the tags necessary. And for each tag, I also have the tag name. So yet again, I don't have to run that query again. So if I actually run a single query on this particular container, let's do that right away. I actually can retrieve all the information in a single query, which has an RU consumption of not more than 2.89 RUs. Compare this to the 15 plus RU consumption. Obviously, you're much, much, much more efficient from the consumption perspective. So to compare the performance of the 2 models in the relation model, or relational, quote unquote, where the data would be stored in individual containers, and then you'd run probably at least 5 queries to get the category name, the name of the products within the category, the product tags, and for each of the product and their name, obviously. The total was over 15 RUs, or would be over 15 RUs. Now, with the same information, literally the same information, you run 1 query, and the request charge is roughly of 2.9 RUs. So the benefit isn't just lowering the cost of a NoSQL design like this model, but this type of design is also faster because it requires only a single request. And further, the data itself is served in a way that's likely going to be rendered on a single web page. This means that there is going to be less code to write, to maintain, to downstream in your e-commerce application.
That's absolutely key, Alex. And I was going to bring up that same point, is for the lazy developer in all of us, not only is this faster and cheaper, but the code is way simpler, right? You're essentially just going to take the result of this query and deserialize it into your complex hierarchical POCO object, where you've got a base class of something and then a enumerable list of orders or products or tags, whatever it is. And then you're going to ship that back via some REST API to your front end. And then that your UX guy will have basically written all the code to render all that stuff on a page. So way simpler, less code. You're spending more time relaxing in a lounge chair than you are debugging and figuring out your live sites.
It definitely is simpler, but we got to be fully honest here. We have duplicated the data, right? So now we need to keep the data in sync. What happens if a category name changes? All the products and the product documents would have to change. And I'm sure you actually have a solution for us, Mark.
I do. In fact, that's our next step in this exercise. What a great segue, Alex. Love it. So let's look at, I'm going to talk about how to implement the relational or the referential integrity here that we've talked about here. And I'm going to do it using change feed. So what I've got here is I've taken and I've cloned the repo that is sitting within our exercise. And I'm just running this here locally because I like running things locally. And what we're going to do is I'm going to show you how to complete the code for the change feed in here. Following on exercise here. So the first thing I want to do is I want to go and find the line where this thing sits. What's that? What are you doing here? Oh, it's doing Control F. I want to Control G. Sorry. So we're going to go to line 603 here. And here you can see here's the function for my change feed. So one thing I want to call out here is we implemented this thing in a way that you wouldn't normally do this. This thing would normally be sitting in its own process. This thing is running in process on a thread within here, and we did it because of the constraints of the lab environment. But that being said, this is our change feed code. It would be the same no matter if it was sitting in its own app or not. And so a couple of things we want to do in here is I'm going to walk through some of these things. So I've got a reference to a database, and then change feed always in its implementation has generally two containers it's monitoring. It's always going to have one that it's listening to. And in this case, this is our product category container. And also because we're affecting a change here by virtue of trying to maintain referential integrity, we have a second container reference we have here, product, which is where we're going to affect the change when we see a change or listen to a change on product category container. So a couple things I want to do here is let's update this so that I've got the right names in here. So I've got my product category container in here, and then I've got this other one. This is product within here. Good. And then next is I need to have a reference to our what we call Lisa's container. Now, Lisa's container is kind of the magic in how this works. And what it does is that it provides kind of a checkpoint for the last time that change feed went and read from it. So the way this works behind the scenes is change feed is essentially kind of a log of LSNs or log sequence numbers. That's basically an incrementing number for data written to a database in the order it was written. The Lisa's container maintains the value of that LSN for the last data that was written. So when it goes and looks, it says, hey, have I got anything new since the last time I've checked here? And it checks the Lisa's container. It says, oh, yeah, you do. And then what we do is inside our SDK, we go and fetch all that data for you and then bring it to this thing that you define here. This is called input here, but it's essentially a delegate where it's going to deserialize data out of this read-only collection. And here we're listening to a single collection called product category. So we're going to deserialize that into our POCO for that, which is product category. Okay, now what we're looking at here is we've got a new list of tasks. Within change feed, you could have one or more items within the change feed since the last time it was checked. It generally runs like every second. So you could have obviously more than one thing that was written over that second. So we want to create a list of tasks because we're going to go and execute all the things that we want to do on here for this data and do it via this list of tasks here. So first thing, I need to write some code to capture all the data for that and then add it to our task list. So I've got a little to do here and I'm going to paste that in here. And here you can see, so within my input, I've got a product category item. And then I'm going to extract the category ID and the category name. And then I'm going to call this function via task.add called update product category name. And I'm going to pass in my product category container reference, the category ID, and my new name. Presumably that's what I'm seeing is the new name within here. And then after all of those are added to the list, I'll just call when all on there and then allow those to go ahead and execute. Okay, further down, I've now got another function here. Here is my update product category name. Okay, so this is what we're going to call to enforce that referential integrity, right? So I see a change on product category. I want to take that change and I'm going to call this function and then make that change happen. So first thing I'm going to do is I'm going to run a query against my category, assuming my product container for that category ID. So I'm going to get all the products for that category because I'm going to go change them all. And then I'm going to create this query item iterator here with the partition key. This is my query definition. And then I'm going to loop through all of those within here. So as I call has more results in a while loop here, I'm going to then get a response to that. And then I'm going to do some more changes here. And then I'm going to call update. So the changes I'm going to do is this here. So I'm going to loop through all the products that I got in that response object, right, for my query. And then I'm going to keep a little count here. And I'll show you why when I run this thing, because I want to make sure that I've got an accurate count for everything I update. I'm going to update the product category name to the category name that I've passed in. So this is the new updated category name. And then I'm going to call replace item async. This is our update function. within there. And that takes the partition key value, which is our category ID, which is why I passed that in, also used in that query. And then the product ID as well I need. And then, of course, the updated product itself that I've now updated with a new category name. Okay, so then within there, I've got this all done within there. So let's go to this in here. I'm going to call exit, and let's do .NET build within here, and I'm going to build that. And cross your fingers, Alex. We're going to run it. So .NET run.
So whilst you're running this application, I do want to bring in like a nasty shout out and segue to the previous episodes that we have had, especially on change feed. If people want to learn more about it, I think that recording actually is totally worth your time if you're interested in change feed and how you can learn more about it. It's all available on YouTube, of course.
Yep. Okay, so building and starting change feed processor. So we'll go ahead and come back. Okay, now I'm going to run my code. So I'm going to update the product category name here. So I'm going to call B, or press B. And here you can see I've done a count. I've got 11 products here in my category called accessories, tires, and tubes. So what I'm going to do is I'm going to make a small change to my category name, and I'm going to rename that category and replace the and with an ampersand. And here you can see change feed is already run, and you can see one change received. This is part of the log or standard output that we had in our change feed here. And then here you can see also updated 11 products with the updated category name, accessories, tires, ampersand, tubes. So there you go. We've made our change. So now I'll rerun that thing, and you can see here's my product category count 11, right, within that category with my new category name. Now let's do this. I'm going to change it back to the original in case that was too fast for you. And here you can see just how fast that worked in there, renaming those product categories across all the products within that category name within there. So that's maintaining referential integrity using change feed, which I think is just super cool. I very much love that.
I couldn't agree more. I do have a question, though. Would you recommend people change data and documents within the data from the client itself, or call a stored procedure instead? Because we do have stored procedures in Cosmos-DB as well.
If you're going to change data, how would I recommend you make the change to the product category or the data?
That's pretty much the question, yeah.
I don't think it matters much. I would not use the portal for doing CRUD operations in general. I mean, Cosmos is meant to be interacted with using an SDK primarily. There are tools, of course, on it that you can use to look at and edit data. But yeah, I would probably write a little app, but that's just me to do it. So, but you could do it in the portal and then just save the document back. That'll trigger it in there. So yeah, for sure.
There's another question from Chris on YouTube, actually. Can change feed update more than one document where the product category name could be in other collections? So all needs to be done, and all needs to be done in a single transaction so that they all get updated at once?
Sure. You could do anything. Once you've got data in change feed, just define more things to go and add to your list of events to go and execute, and then call and then do a when all on that. So you could propagate that change to absolutely anything. You could even do stuff like, and I know someone would love this, is you could call things like event grid and then create a bunch of subscribers to event grid, and then they could go and do anything you want on it. Isn't that right, Tom? I don't know if he's listening, but I just felt like calling him out. So, all right, where are we? Now what we're going to do is, the second thing I want to show you is denormalizing aggregates. And there's a couple of things here I want to show you. So first, I want to show you how to create new orders and update customer using transactions. So this is using what I consider one of the coolest features in our SDK. It's been out for a couple of years now, is transactional batch. Before we had transactional batch, if you wanted to do transactions in Cosmos-DB, you had basically a choice of stored procedures, which are written in JavaScript and are hard to debug, and not my favorite way of doing it. I much prefer doing things using like a .NET SDK or Java or something where I've got full kind of like a Visual Studio or IDE experience that I can go and run these things and debug them and step through and all that stuff. So here I've got some code here. I've got a customer ID that I'm kind of pre-selecting because I know this customer. And then we're going to create read item async. So we're going to do a point read for this customer, which is, by the way, the most efficient way of getting data in and out of Cosmos. Is if you want to get a single record of data, a single document, and you know the ID and the partition key, use this function, read item async. Anything that's less than anything that's a kilobyte or less of data, you can get it for 1 RU and guaranteed less than 10 milliseconds at P99.
Rather than actually running a select star when predicate.
Rather than running a query. Yeah, and the reason is because read item async goes directly to our backend store. It does not go through a query layer versus where if you query data, you're basically going through extra layers in there. All right, first thing I need to do is I got to get my customer, and I got him here, right? I need to increment sales order count. So I'm going to call customer.salesorderCount ++, and that is going to increment that property on that customer object in preparation for a new order here. So, okay, so now I'm going to go through, I'm going to create a new sales order. So I've got a new sales order class here, create a new instance of it. I'm just plugging in some values here. By the way, I have to put my type in, right? Because I'm co-locating that with customers. So I need a type to discriminate. Customer ID, of course. My order date is now, and that's going to be in our ISO format that we require. Ship date is empty because obviously it hasn't shipped yet. And then here's a new list of sales order details. I've got a mountain bike frame in here, and I got some socks. So I bought a mountain bike frame and a couple pairs of socks. Now, next thing I need to do is I need to write the code that is actually going to call the transactional batch and insert my new order and update my customer record with my new customer order number. So I've got some more code here. And I'm going to call this. So I've got transactional batch response equals container.create transactional batch. Okay. Now, remember I said everything is scoped to a logical partition key. So guess what? One of the values that you have to pass is the partition key, right? So there's my customer ID. And then I can use this using this fluid interface here. I can call up to 100 different things within this transaction. And that'll all execute or successfully or fail together, no matter if one of these things fails in here. So here I'm going to do create item. So there's my new sales order that I just created, and I passed my sales order object. And then I'm going to call replace item, right? That's our update. And I'm going to pass in my customer ID and my customer object in there. And then I'm going to call execute async. And then here you see I've got a status code, and I can just output say, okay. That's working fine here. So I think that's all I need within here. So, I want to do call my top 10 customers in here. So here I've got my query within here. You can see select top 10, first name, last name, sales order count. Remember, I need to use the discriminator property. So where type equals customer, and then order them with sales order count in descending order, and then I'm going to loop through those things there. Okay, I think that's it. How are we doing on time? We're way over, as always, with anything with me associated with it. I have a hard time staying on time. .NET Run. But you're getting good knowledge, hopefully. So hopefully this is a good use 100%. Of your time. Okay, so I first want to I'm going to query for a customer and all their orders here. So I'm going to call menu C, and this should be the customer that I'm going to create an order on here. So we've got Destiny Peterson is our customer here, and here's her address. There's her password, and you can see sales order count of 2. Now let's double check, because the query I called here queried everything. It queried the customer and the sales order. In fact, I should show you that query because there's a little tip or trick I want you to know. So here's a product in here, sales order. I got another mountain bike frame, it looks like, and then some shorts in here. So there's 1, 2, 3 products in here. And then I got another order, and I got another mountain bike frame. This person's really into biking. So there we go. Now let's call our transactional batch. So I'm going to create a new order and update the order total. So I'll call D here, and there we go. Now let's query for the customer and all their orders. And let's go back. And here's Destiny Peterson address. And oh, that did not update. That's not right. Oh, wait, maybe it's lower. Hold on.
Can you do me a favor, actually, and go back in code? I think we missed one part.
Oh, really?
Just a hint.
Maybe. Hold on.
So if you actually open up, yeah, that method right there. Oh, no, there it is. Count plus plus.
Yeah, that should have worked. And there's my execute async.
Indeed.
This is very troubling. I am not quite sure why.
Did you sacrifice any production VMs in favor of the demo gods?
No, I forgot.
That must be it.
You think it is? That's a bummer. Let's create a new order. Sorry, it's going to take a second because it's... oh, that's different. Let's try this again. See? Okay. I think I got it. So, sales order count. Here we go. Destiny Peterson. Sales order count is 3. I guess they got my delivery of sacrificed VMs. Little delay in my order there from my tropical forest e-commerce company there. So there's one order. Here's another one. And there's my third. There's my mountain bike frame and my socks. Okay. So guess what? Not only does this work when you create an order, but it also works if you delete an order. So we'll call F here. And let's go and run C. And guess what? I'm back to 2 now for that order, right? Because I can call delete on there and do that in a transactional batch as well within there. Okay. Now let's show you my last one, query top 10 customers. I'll run that E. Now that I've got my data aggregated denormalize my aggregates within my customer records there. You can see I could run this query and get back that data in a reasonable amount of time. And one of the things I want to point out here is this is a cross-partition query, right? I just called a query that's got a bunch of customers in it out of the customer container, right? Which is partitioned by customer ID. And I just said, give me the top 10 of those, right? And I didn't pass in a customer ID on it, right? So this was a cross-partition query. Now, I know we say, hey, don't do cross-partition queries. What we really mean, and to provide more kind of precise guidance on that, is avoid them for high concurrency queries and very large collections for high concurrency queries. They're okay once in a while. Like I would probably run a query like this maybe once a month. Maybe I'm going to send out a gift certificate to my top 10 customers or something like that. That's okay. But this is not something you would run at high concurrency or high volume, right? If every time a customer logs in, I have to run a cross-partition query, that's bad design. That's not going to scale. But something like this, it doesn't necessarily need to scale. But what we did is we made it possible to get this in as efficient a manner as possible by using the transactional batch, by designing our model to store that denormalized aggregate within the customer record. So, okay. How are we doing? 10 minutes left is what I see from our friendly.
I think it was like a few minutes ago.
Was that a few minutes ago? 120.
Yeah.
6 minutes and 30 seconds. Okay. Well, I think that's it from me from an exercise perspective. I guess if we want to go back to our slides here, we can kind of wrap things up.
We actually have a knowledge check, and we could probably take at least the first question, if you don't mind.
Yeah, we don't want to spoil it for everyone, right?
Absolutely. So I do want to remind people that they can obviously chat in the chat window, but they can also vote. And in real time, we're going to get their answers as they answer this question as well. And I'm going to read out loud the question. In azure-cosmos-db, what would be the most optimum way of managing referential integrity between different containers? Is it A, when your app creates any changes to one container and also make sure it duplicates the changes on the reference container? Or is it B, create an azure-cosmos-db function that periodically searches for changes done to your container and then replicate those changes to the reference containers? Or is it C, Use an Azure function trigger for an azure-cosmos-db account to leverage on the change feed processor to update the reference container. Interesting question.
Hold on, let me make my I'm thinking face and my finger.
We got to leave some seconds there for audience to answer. I think it's almost a no-brainer, especially after seeing your fantastic demo there on change feed and leveraging change feed, where obviously what you did, long story short, with the processor and everything else, was to constantly not check, but rather be triggered whenever a change occurred to either of the documents. And then the thing I really do appreciate is the way you're manipulating the document, as in you want to calculate some aggregates, you have that. You want to update some part of the document or maybe other documents, you can also do that. And this ensures that you have, well, we call it referential integrity, but effectively put simply in popular English, it just ensures that all of our data is always in sync and we don't have that nasty world of denormalization where one part of data is incorrect or it's different from the other part of the data, and you no longer know what's correct or what's valid.
And you don't even need Azure Functions to do this, right? Like I was just using a regular console app hosting the change feed. So if you want to go down to the low-level change feed processor, you absolutely can, and you can host that in anything. It could be an empty function controller or container, or it can be like a little container app, or it can be, my God, if you want to fire up AKS and deploy the thing in a little Docker container and run it that way, then man, go nuts. You can use any compute to host the change feed processor. Azure Functions triggers for Cosmos DB provide kind of a very easy like a simple way or simpler way of doing that without having to do a bunch of the plumbing underneath there. So
yeah, full disclosure here, I'm a major fan for Azure Functions, and that would be my first choice at all times. But I fully agree with you; it can be anything, anywhere, running anywhere, even, right?
Yep,
it doesn't even have to be Azure.
And by the way, you don't even need it just for maintaining referential integrity. Change feed you can use to do any CDC or any event-driven types of applications. It is absolutely the heart and soul for doing like microservices using a database like Cosmos. So
fantastic. Really now, we only have a couple of minutes left, and because of that, I do want to wrap up and ask you one very important question as we're wrapping up. But we have learned quite a few today. The audience will definitely go over the Microsoft Learn modules at their own pace and recap everything that we have touched on today. We have had a very long session, a bit theoretical, but also a lot of knowledge, and I'm sure everyone appreciates the fantastic learnings that we have had. First, we have learned about managing relationship between data entities by using advanced modeling and partitioning strategies. You have actually also told us more on maintaining the referential integrity of your data by using the change feed, and I really appreciate that part. We have also looked into implementing pre-aggregating and normalizing data strategies to improve data model performance and scaling, as well as optimizing storage and compute by mixing entity types in a single container. And obviously, people can head out and learn more about these, can't they?
Yeah, so feel free to go check out AKAMS at the Learn Live link there. You take a screen cap of that, or just hold your phone right up to the QR code there and snap away. And you can go and follow along and learn about all these awesome techniques that we've got.
And I do want to remind everyone that this is actually part of a series. So today we have learned about designing a data partitioning strategy, and the next episode that we're going to have, part of the series, is on configuring replication and managing failovers in Azure-cosmos-db. Another fantastic topic that I'm really looking forward into learning more. Now, as we're wrapping up, Mark, really quick question. I really want to take this opportunity and ask you this. We saw how Cosmos DB can do transactions. We have learned about, in the previous episodes, about store procedures, about indexes, in a NoSQL world, in a NoSQL database. And we've even learned that there are joins, right? And much more as well. This begs the question, is Cosmos DB going to take over the world and replace all the data persistence technologies one day? But jokes aside, what's next for Cosmos DB, really?
As much as I would love that to be the case, I think that the future is a world of cohabitation of different database technologies that are designed for the job they're really best suited for, whether it's database like ours in a NoSQL world, or even relational, whether it's SQL or Postgres or MySQL or Oracle or even other types of databases as well, like things like OLAP or whatnot. So right tool for the job, right?
Absolutely, polyglot persistency.
That's right.
Really do appreciate you having you with me on this episode, Mark. Learned a lot, had loads of fun. Must say that, and I'm sure our audience have had that as well. Make sure to follow Mark on Twitter. You have his Twitter handle, and let's keep the conversation going offline. With that being said, it was a great pleasure to have you here with me, and everyone, stay safe.
Alex, thank you so much. Great being here. Thank you very much, everyone.